Hey everyone, welcome to more calculus. Today we're going to be starting on our chapter 7 now, and this is going to be about logistic growth. That's the main topic here, but of course we're going to have to start with something that's not logistic growth so we can get into it. So let's start by looking at some differential equations that are very specific. Here's more about diseases, and the disease that we're going to be concerning ourselves with is something called dragonpox, which is a potentially fatal contagious disease that occurs in wizards and witches. Its symptoms are presumably similar to the muggle illnesses like chickenpox, and then it goes on to have some symptoms of this. But we're going to go ahead and take a look at what we mean by a partial fraction decomposition. A partial fraction decomposition basically takes a rational function like the one you see here, and then it turns it into a sum of two or more rational functions, each with a degree on the denominator, which that's linear. Here in BC, we only really talk about linear partial fractions. So the first thing you're going to do is factor your denominator. If your denominator is not factorable, there's not really much you can do here. So I think we got 2x, x, 1, and 3. And wow, that's great. Now that we have it factored, oh, and look, it was already factored over here for us. Imagine that. We have these two linear factors. And what we're going to do is we're going to multiply by the denominator on the left side. So we're going to multiply both sides by 2x minus 1 multiplied by 2x minus 3. So we're multiplying that on the left and the right side. It's kind of hard to see because, this up here, this is the left side, and this over here is on the right side. So let's take a look at the left side. If I multiply, basically this denominator cancels, and I'm left with just x minus 3. And on the right side, what happens is, well, when I distribute this to the first term, I'm going to factor out, I'm going to cancel out the 2x minus 1. And that's going to leave me a multiplied by x minus 3. If I do something similar, factor again, or not factor, distribute into the second partial fraction. That's the partial fraction part here. The x minus 3 is going to cancel, and I'm going to be left with 2x minus 1. So really quickly, I've gone ahead and I have simplified this so that it is a linear, basically, expression. So this may look like we have 3 unknowns and 1 equation, but in actuality, x is a variable. A and b are going to be parameters. Now those values of a and b need to be the same no matter what our value of x is going to be. So what we're going to do is we're going to choose values of x which are convenient to solve. So once again, x is a variable, a and b are parameters. So regardless of what number I choose for x, the equations should be correct, have the same values of a and b. So the first number we're going to try is, what if x is equal to 1/2? Okay, if x is 1/2, that means that I'm going to go ahead and substitute 1/2 for all my values of x. 1/2 minus 13, that's negative 12.5. This is 1/2 minus 3, and 1/2 minus 3 is negative 2.5a. And this over here, that's 0. So choosing that 1/2 allowed us to make one of these two partial fraction pieces equal to 0. Doing the division, we get that a is 5. And then we're going to do the exact same thing here for b, but this time we're going to substitute a 3. So every place that has an x is going to be a 3. 3 minus 13 is negative 10. 3 minus 3 is 0, so this cancels out. And then this is 6 minus 1, or 5, so that's 5b. So b is negative 2. Now let's go back to the very beginning here and take a look at this expression. I now have values of a and b that make this expression true. So a is 5 and b is negative 2. This is the partial fraction decomposition. Okay, so 5 and negative 2, and we are off. We now have a partial fraction decomposition, and we can, well, the next part here is we need to use that partial fraction decomposition. And the way you use this is by saying, well, if I wanted to take the antiderivative, if I want to take an antiderivative of x minus 13 over 2x squared minus 7x plus 3, that's really the same as taking the antiderivative of the two partial fractions. Now, each of these partial fractions will be easier to integrate than our original function. So let's start by integrating our first partial fraction. So in order to integrate this first partial fraction, we're going to have to use a u substitution because we have 2x minus 1 on the denominator. So if u is 2x minus 1, du will be 2 dx. Solving for dx, we get dx is going to be half of du. Now we're going to substitute. This is the substitution method. So the antiderivative of 2x minus 1 dx, that's 5 over u. Remember that your 2x minus 1 is the same thing as u from here. And then your dx, that's the same thing as 1/2 du. Now the integral here, the 5 and the 1/2, that's where the 5/2 comes from. The integral of 1 over u is a natural log of the absolute value of u. And then we just substitute back in and we get 5 over 2, natural log of 2x minus 1 plus that constant. Now we're going to do the second partial fraction. It's just a bit easier than this one. Taking a look at this, the u is going to be x minus 3, that's the denominator. Du is going to be dx, so really this isn't going to, quote, cost us anything when to make the substitution. So we'll get negative 2 over x minus 3 is going to be equal to negative 2 over u du, which is negative 2 natural log of u. And of course, remembering that u is x minus 3, we get minus 2 natural log of x minus 3. So let's put it all together over here. We can see that the antiderivative of the first partial fraction is 5/2 natural log of 2x minus 1. That's from here. The antiderivative of the second partial fraction is minus 2 natural log of x minus 3. We can do some further simplification here, but no, let's take a look at that simplification. We've got the natural log of the square root of 2x minus 1 to the 5th power. Remember, that's 2x minus 1 to the 5/2 power from our properties of logs. And then we also have the natural log of x minus 3 squared. In both cases, we no longer need the absolute value because the square root always returns a positive value, and a square, returns a positive value also. So now we can just combine this with another law of logs. There we go. Putting it all together, we have the natural log of the square root of 2x minus 5 to the fifth over x minus 3 squared. So that's usually the way that you're going to see this expressed on a free multiple choice question. Free response wise, if you're just having to write out an answer, the previous one, any of the previous ones are good enough. So that's taking this partial fraction from beginning to end. And now we're going to look at some more properties of partial fractions. So the main thing here that we need to talk about is that the degree of the numerator needs to be smaller than the degree of the denominator. So we have this example here where we have 3x to the fourth plus 1 over x squared minus 1. Well, here the degree of the numerator is bigger than the degree of the denominator. So we do some polynomial division to get 3x squared plus 3 plus 4 over x squared minus 1. Now when we take a look at this 4 over x squared minus 1, this is perfect for a partial fraction decomposition. Now the antiderivative of 3x squared plus 3, that's pretty easy. We did that weeks ago. So now let's go ahead and go through this exercise to figure out our partial fraction. First thing is to factor that denominator. We got x minus 1 over x plus 1. And then now we're going to multiply both sides by x minus 1, x plus 1. And what's that? The effect of that is going to be to cancel the numerator on the left, and on the denominator, there's that first canceling. We have a multiplied by x plus 1 plus b multiplied by x minus 1. That's what's going to happen there. Let's figure out convenient values of x so we can solve for a and b. The first one I'll pick is x equals 1. So when x equals 1, 4 is going to be equal to 2a. 1 plus 1 is 2. And that tells me that a equals 2. And then when x equals negative 1, 4 is going to be equal to, this is going to be 0, and the second term here is going to be negative 2b. So b is going to equal to negative 2. Some students say, hey, is that a pattern? 2 and negative 2? No, there's no pattern like that here. If one's 2, that doesn't mean the other one's going to be negative 2. So we're going to put that all together. On top of x minus 1 is a, and a is, where is it? A is 2. And on top of x plus 1 is b, and b is negative 2. And now, of course, we can integrate. So 3x to the fourth plus 1 over x minus 1, that is going to be equal to, what was that, 3x squared plus 3? Let's make sure I got that right. Yeah, 3x squared plus 3 plus 2 on top of x minus 1 plus negative 2 on top of x plus 1. And we can integrate both sides because that's what we're going to need to do eventually. And then integral of this one, then integral of this one. So we're going to integrate all three of these together, and none of these are difficult to do. This first one here is x cubed plus 3x. This second one here is 2 natural log of x minus 1. This one over here is minus 2 natural log of x plus 1. Then we have our constant. These should be absolute values. We're going to raise our power in our logs. So this is x cubed plus 3x plus the natural log of x minus 1 squared. No longer need the absolute value because of the square. Minus the natural log of x plus 1. That doesn't look like a 1. Squared. Same thing. No absolute value needed. And that simplifies into x cubed plus 3x plus the natural log of x minus 1 over x plus 1, whole thing squared, plus constant. So that takes us beginning to end with our partial fraction decomposition, including our antidifferentiation. So here are the important ideas for partial fraction decomposition. What it does is it transforms a rational function into a sum of fractions. Calculus BC, we're only going to work with linear denominators in our decomposition. And if the degree of the numerator happens to be bigger than the degree of the denominator, then you're going to need to do some synthetic division. The degree of the denominator must be greater than the degree of the numerator. So let's check this one out. We'll start with a partial fraction decomposition. This is going to be, oh, well, look at this. This is x minus 2, x plus 2. And this will be, now notice that there are 3 partial fractions we're going to have to do here. So our first partial fraction will be a on top of x minus 2. Our second partial fraction will be b on top of x plus 2. And our third partial fraction will be c on top of x minus 1. Okay. Now we're going to multiply the left and the right by our denominator. Remember, on the left side, we're just going to cancel that denominator. And on the right side, on our denominator, we're going to cancel out the x minus 2. And what's going to be left here is going to be x plus 2, x minus 1a. Plus, when I distribute over here on the left, on the second partial fraction, the x plus 2 will cancel out. We saw that last time. And we're going to get x minus 1, x minus 2, x minus 1, b. And if you can see the pattern here, our c is going to be multiplied by the other 2 denominators. So x minus 2, x plus 2, c. Let's figure out our values here. And the first one I'm going to pick, let's pick x equals 2 to start off with. When x equals 2, we're going to get 4 equals 4a. And that means that our a is equal to 1. When x equals negative 2, we're going to get 36 is equal to 12b. Sorry, I should have written it as 0a plus 12b plus 0c, meaning our b is equal to 3. And lastly, when x equals 1, right? Yes, when x equals 1, we get negative 6 equals negative 3c, so c is equal to 2. So now I'm just going to go up here and I'm going to replace all of these. No, I should rewrite the entire thing. Okay, so the integral of, we're going to take it all the way to the integral, of course, 6x squared minus 8x. That's going to be equal to the integral of 1 over x minus 2 dx. Remember, a is 1. A is 1. That's plus b, which is 3, over x plus 2. And c, which is 2, over x minus 1. Notice how these all match with what I wrote over here, which I like to think of as my key. Without that, I might mix up the numerators, so I try not to do that. Now the right side's pretty easy to take the antiderivative of. These are all linear terms. There is no coefficient for x on the denominator, and all the x's are positive, so it's just natural logs. So the natural log of x minus 2 plus 3 times the natural log of x plus 2 plus 2 times the natural log of x minus 1 plus constant. And looking at that, remember we can take all of those coefficients and make them powers and then combine this all. So we're going to combine it all. That's x minus 2 multiplied by x plus 2 cubed multiplied by x minus 1 squared plus constant. We're not assured that this is always going to be a positive product because we do have a third degree and a first degree power here. So we're not sure if this is going to be positive or negative. So we have to leave the absolute values. So that's our look at partial fraction decomposition and the related antiderivatives that go with them. Good luck, and I'll see you next time here for more calculus.